An atomic battery, nuclear battery, radioisotope battery, or radioisotope generator uses energy from the decay of a radioactive isotope to generate electricity. Like a nuclear reactor, it generates electricity from nuclear energy, but it differs by not using a chain reaction. Although commonly called batteries, atomic batteries are technically not electrochemical and cannot be charged or recharged. Although they are very costly, they have extremely long lives and high energy density, so they are typically used as power sources for equipment that must operate unattended for long periods, such as spacecraft, pacemakers, underwater systems, and automated scientific stations in remote parts of the world. Nuclear batteries began in 1913, when Henry Moseley first demonstrated a current generated by charged particle radiation. In the 1950s and 1960s, this field of research got much attention for applications requiring long-life power sources for spacecraft. In 1954, RCA researched a small atomic battery for small radio receivers and hearing aids. Since RCA's initial research and development in the early 1950s, many types and methods have been designed to extract electrical energy from nuclear sources. The scientific principles are well known, but modern nano-scale technology and new wide-bandgap semiconductors have allowed the making of new devices and interesting material properties not previously available. Nuclear batteries can be classified by their means of energy conversion into two main groups: thermal converters and non-thermal converters. The thermal types convert some of the heat generated by the nuclear decay into electricity. An example is the Radioisotope thermoelectric generator, RTG, often used in spacecraft. The non-thermal converters, such as Betavoltaic cells, extract energy directly from the emitted radiation before it is degraded into heat. They are easier to miniaturize and do not need a thermal gradient to operate, so they can be used in small machines. Atomic batteries usually have an efficiency of 0.1 to 5%. High-efficiency Betavoltaic devices can reach 6 to 8% efficiency. Thermal conversion, thermionic conversion. A thermionic converter consists of a hot electrode, which thermionically emits electrons over a space charge barrier to a cooler electrode, producing a useful power output. Cesium vapor is used to optimize the electrode work functions and provide an ion supply by surface ionization to neutralize the electron space charge. Thermoelectric conversion, a radioisotope thermoelectric generator, RTG, uses thermocouples. Each thermocouple is formed from two wires of different metals or other materials. A temperature gradient along the length of each wire produces a voltage gradient from one end of the wire to the other, but the different materials produce different voltages per degree of temperature difference. By connecting the wires at one end, heating that end but cooling the other end, a usable but small millivolts voltage is generated between the unconnected wire ends. In practice, many are connected in series or in parallel to generate a larger voltage or current from the same heat source as heat flows from the hot ends to the cold ends. Metal thermocouples have low thermal to electrical efficiency. However, the carrier density and charge can be adjusted in semiconductor materials such as bismuth telluride and silicon germanium to achieve much higher conversion efficiencies. Thermophotovoltaic conversion. Thermophotovoltaic (TPV) cells work by the same principles as a photovoltaic cell, except that they convert infrared light rather than visible light emitted by a hot surface into electricity. Thermophotovoltaic cells have an efficiency slightly higher than thermoelectric couples and can be overlaid on thermoelectric couples, potentially doubling efficiency. The University of Houston TPV radioisotope power conversion technology development effort is aiming at combining thermophotovoltaic cells concurrently with thermocouples to provide a 3 to 4-fold improvement in system efficiency over current thermoelectric radioisotope generators. Stirling Generators. A Stirling radioisotope generator is a Stirling engine driven by the temperature difference produced by a radioisotope. A more efficient version, the advanced Stirling radioisotope generator, was under development by NASA, but was canceled in 2013 due to large-scale cost overruns. Non-thermal conversion. Non-thermal converters extract energy from emitted radiation before it is degraded into heat. Unlike thermoelectric and thermionic converters, their output does not depend on the temperature difference. Non-thermal generators can be classified by the type of particle used and by the mechanism by which their energy is converted. Electrostatic conversion. Energy can be extracted from emitted charged particles when their charge builds up in a conductor, thus creating an electrostatic potential. Without a dissipation mode, the voltage can increase up to the energy of the radiated particles, which may range from several kilovolts for beta radiation up to megavolts, alpha radiation. The built-up electrostatic energy can be turned into usable electricity in one of the following ways. Direct charging generator. A direct charging generator consists of a capacitor charged by the current of charged particles from a radioactive layer deposited on one of the electrodes. Spacing can be either vacuum or dielectric. Negatively charged beta particles or positively charged alpha particles, positrons or fission fragments may be utilized. Although this form of nuclear electric generator dates back to 1913, few applications have been found in the past for the extremely low currents and inconveniently high voltages provided by direct charging generators. Oscillator transformer systems are employed to reduce the voltages, then rectifiers are used to transform the AC power back to direct current. English physicist H.G.J. Moseley constructed the first of these. Moseley's apparatus consisted of a glass globe silvered on the inside with a radium emitter mounted on the tip of a wire at the center. The charged particles from the radium created a flow of electricity as they moved quickly from the radium to the inside surface of the sphere. As late as 1945, the Moseley model guided other efforts to build experimental batteries, generating electricity from the emissions of radioactive elements. Electromechanical conversion. Electromechanical atomic batteries use the buildup of charge between two plates to pull one bendable plate towards the other until the two plates touch, discharge, equalizing the electrostatic buildup, and spring back. The mechanical motion produced can be used to produce electricity through flexing of a piezoelectric material or through a linear generator. Milliwatts of power are produced in pulses depending on the charge rate, in some cases multiple times per second, 35 Hz. Radiovoltaic conversion. A radiovoltaic device converts the energy of ionizing radiation directly into electricity using a semiconductor junction, similar to the conversion of photons into electricity in a photovoltaic cell. Depending on the type of radiation targeted, these devices are called alphavoltaic AV, betavoltaic BV, beta V, and/or gammavoltaic GV, GUG&V. Betavoltaics have traditionally received the most attention since low-energy beta emitters cause the least amount of radiative damage, thus allowing a longer operating life and less shielding. Interest in alphavoltaic and more recently gammavoltaic devices is driven by their potential higher efficiency. Alphavoltaic conversion. Alphavoltaic devices use a semiconductor junction to produce electrical energy from energetic alpha particles. Betavoltaic conversion. Betavoltaic devices use a semiconductor junction to produce electrical energy from energetic beta particles, electrons. A commonly used source is the hydrogen isotope tritium. Betavoltaic devices are particularly well suited to low-power electrical applications where long life of the energy source is needed, such as implantable medical devices or military and space applications. The Chinese startup Betavolt claimed in January 2024 to have a miniature device in the pilot testing stage. It is allegedly generating 100 microwatts of power and a voltage of 3 volts, and has a lifetime of 50 years without any need for charging or maintenance. Betavolt claims it to be the first such miniaturized device ever developed. It gains its energy from the isotope nickel-63, held in a module the size of a very small coin. As it's consumed, the nickel-63 decays into stable, non-radioactive isotopes of copper, which pose no environmental threat. It contains a thin wafer of nickel-63 providing beta particle electrons sandwiched between two thin crystallographic diamond semiconductor layers. Gammavoltaic conversion. Gammavoltaic devices use a semiconductor junction to produce electrical energy from energetic gamma particles, high-energy photons. They have only been considered in the 2010s, but were proposed as early as 1981. A gammavoltaic effect has been reported in perovskite solar cells. Another patented design involves scattering of the gamma particle until its energy has decreased enough to be absorbed in a conventional photovoltaic cell. Gammavoltaic designs using diamond and Schottky diodes are also being investigated. Radiophotovoltaic optoelectric conversion. In a radiophotovoltaic RPV device, the energy conversion is indirect. The emitted particles are first converted into light using a radioluminescent material, a scintillator or phosphor, and the light is then converted into electricity using a photovoltaic cell. Depending on the type of particle targeted, the conversion type can be more precisely specified as alpha-photovoltaic, APVV, beta-photovoltaic, BPV or BPV, or gamma-photovoltaic, GPV or GAMPV. Radiophotovoltaic conversion can be combined with radiovoltaic conversion to increase the conversion efficiency. Pacemakers Medtronic and Alcatel developed a plutonium-powered pacemaker, the NUMEC NU5, powered by a 2.5 Ci slug of plutonium-238, first implanted in a human patient in 1970. The 139 NUMEC NU5 nuclear pacemakers implanted in the 1970s are expected to never need replacing, an advantage over non-nuclear pacemakers, which require surgical replacement of their batteries every 5 to 10 years. The plutonium batteries are expected to produce enough power to drive the circuit for longer than the 88-year half-life of the plutonium-238. The last of these units was implanted in 1988 as lithium-powered pacemakers, which had an expected lifespan of 10 or more years without the disadvantages of radiation concerns and regulatory hurdles, made these units obsolete. Betavoltaic batteries are also being considered as long-lasting power sources for lead-free pacemakers. Radioisotopes used atomic batteries use radioisotopes that produce low-energy beta particles or sometimes alpha particles of varying energies. Low-energy beta particles are needed to prevent the production of high-energy penetrating bremsstrahlung radiation that would require heavy shielding. Radioisotopes such as tritium, nickel-63, promethium-147, and technetium-99 have been tested. Plutonium-238, curium-242, curium-244, and strontium-90 have been used. Besides the nuclear properties of the used isotope, there are also the issues of chemical properties and availability. A product deliberately produced via neutron irradiation or in a particle accelerator is more difficult to obtain than a fission product easily extracted from spent nuclear fuel. Plutonium-238 must be deliberately produced via neutron irradiation of neptunium-237, but it can be easily converted into a stable plutonium oxide ceramic. Strontium-90 is easily extracted from spent nuclear fuel, but must be converted into the perovskite form strontium titanate to reduce its chemical mobility, cutting power density in half. Cesium-137, another high-yield nuclear fission product, is rarely used in atomic batteries because it is difficult to convert into chemically inert substances. Another undesirable property of Cs-137 extracted from spent nuclear fuel is that it is contaminated with other isotopes of cesium, which reduce power density further. Microbatteries. In the field of microelectromechanical systems, MEMS, nuclear engineers at the University of Wisconsin-Madison have explored the possibilities of producing minuscule batteries which exploit radioactive nuclei of substances such as polonium or curium to produce electric energy. As an example of an integrated, self-powered application, the researchers have created an oscillating cantilever beam that is capable of consistent, periodic oscillations over very long time periods without the need for refueling. Ongoing work demonstrate that this cantilever is capable of radio frequency transmission, allowing MEMS devices to communicate with one another wirelessly. These microbatteries are very light and deliver enough energy to function as power supply for use in MEMS devices, and further for supply for nanodevices. The radiation energy released is transformed into electric energy, which is restricted to the area of the device that contains the processor and the microbattery that supplies it with energy.